Hey guys, a lot of people have asked me why I'm bearish on quantum computing and why I think that, basically quantum computing isn't worth anything. Well, to understand the thesis, you have to know a little bit about computing, which makes sense. One of the things that you have to understand about computing is the idea of complexity. And complexity is the study of algorithms. And I'm going to try to make this as simple as possible. And after watching this, you'll understand why quantum computers will basically never amount to anything. So if you take a classic algorithm, binary search is one. And binary search sounds complicated, but it's really simple. It's just basically checking whether or not, let's say there's an array, 0, 7, 4, and 3, and you want to check if a variable is a member of the array. So 5 is a member of this array. You can check through binary search, and you would find that it is not a member of this array. I hope that makes sense. And as this list gets bigger, you can imagine the search gets harder. But how hard does it get? And on average, how much time do you have to spend to actually find whether or not this number is in this array? And the simple math of that is something called O notation. So it's big O, and it's something called log n, or log is the natural logarithm 2, so log 2n, and or ln. And so the amount of steps it takes, it sort of gets very easy. So if you had 100 steps, this is basically log 2 of 100. And log 2 of 100 is roughly 6 or 7, right? 2 to the 6th is 64. And 2 to the 7th is 128. So it would take you around 6 or 7 steps to figure out if something is a member of a 100 array list. So it's a pretty nice algorithm. It can figure it out very, very quickly. And so with respect to, I have this array a little, let's make that a 1. So that makes sense. So there's other algorithms that are really hard. So with respect to, so with respect to a tougher algorithm like the traveling salesman problem is something like it's a really complicated algorithm where you have, let's say, 5 or 6 cities, maybe more, and you have to figure out what's the best route for this salesperson to minimize distance traveled. This is a really hard problem, and it's basically factorial time, which is an insanely long time. So as the amount of cities goes up, you get this really insane amount. So I don't want to calculate this too much, but like you could say if there's one city that the algorithm doesn't make any sense. If there's 3, this is really an algorithm designed for larger numbers. But I don't know. We could do this real quickly. Let's say 5 factorial times 5 is 600. So just with 5 cities, we're at 600 steps of the algorithm. And how about, say, 7 factorial times 7, just 2 cities more, and it's 35,280. And this rises exponentially. In fact, it rises in factorial time, which is faster than, is it faster than exponential? So in any event, this goes up very, very quickly. So why do we study this? Well, we have to understand why certain algorithms take longer than others. If you don't use the right algorithm, for example, if you could find an algorithm where you can do the traveling salesman problem, instead of taking 600 steps, you could do it in 60 steps. That'd be an amazing victory. You could do a lot of complicated computer programs much faster. right? Yeah, I thought it was faster than exponential. So, of course, no such algorithm exists as far as we know, but people will still search for it. And this is a very, very, very hard problem to solve. Why is this important? Stick with me. This is really important. There are some algorithms where, for example, in binary search, you could do this in sort of a more naive way. So for integer factorization, for example, let's say I want to factor some biprime. What's a good biprime? I don't know, 81 or something like that. Well, to factor 81, I basically have root of n, O root of n, because I can test every number between 1 and the square root of 81. It turns out that 9, of course, is the answer, but that's the amount of steps I have to take. Now, there is a slightly faster algorithm than this called number field sieve, and it can take a really, really big number and divide it a little bit faster than this. It's still not great, but just a little bit faster. What if I told you there was an algorithm that can take an integer, like 81 or some much larger one, and divide it much faster? In fact, it can divide it almost instantly. Well, you would ask, how can it do that? Because there's only two ways. Either the computer's faster or there's a better algorithm. And in this case, there is a better algorithm, and it's called Shor's algorithm. And with Shor's algorithm, instead of root of n steps, so this is 9 steps, okay, for 81. But let's pick a bigger number. Okay, let's do this one. 69,169, something like that. Well, the root of that number, as we know, is 263 steps. That's a lot of steps. And this just gets bigger and bigger and bigger. Let's say multiplying it again. Make it, 10 numbers, or 50 digits, or 70 digits. The amount of steps starts getting very cumbersome. That's why with RSA, it's a 2048 bit number. And in fact, we may even go to 4096. With crypto, with Bitcoin, it's a 256-bit number, which is about 77 digits. So 10 to the 77th power, you would have to check root of 10 to the 77th, which is 10 to the 38th. No computer can do that, quantum or not. You cannot check 10 to the 38 numbers. You need a smarter way of doing it. And just like if I threw a bunch of index cards at you and said, sort these index cards, there's a smart way to do it and there's a slow way to do it. And you have to know which way. So Shor's lets you calculate this in a different complexity. In fact, here it is, it's polynomial time. So it's O(n) to the third power. So this is really crazy, because if you think about it, n can never, did I draw that bad? There we go. N, no matter how big n gets, it's sort of cabined as to how much it'll really expand. So you can do, let's see. You can do a bit length that will vastly sort of beat a large bit length here. And that's something that, is that's something that I'll sort of show you how it's done in a second, but there's a massive speed up, and it does not come from the computer being faster. That's the key. So how fast are these computers? Well, an NVIDIA chip is around 2 gigahertz clock speed. So it can do one operation in 2 gigahertz. I'm sorry, it can do 2 billion operations in 1 second. Which is what a hertz is. Ion trap computers, yeah, thank you. Missed the log there. I'm sitting here wondering why this thing isn't working. 10,000 hertz is what the IonQ computer can do, roughly, or any ion trap. Whereas an NVIDIA machine or an Intel machine not only can do 2 billion instead of 10,000, but also has multiple cores. And NVIDIA has a lot more cores, thousands of cores per chip. So clearly, it's not because the computer is faster. It's because it can do the algorithm a lot better. So this number took 263 steps. How many steps would it take to do in quantum time? Well, what's the log of log 2 of 263? It's around 17. Log 2 of 169, and then cube that. It's roughly 17. So instead of 263 steps, you can do it in 17 steps. And that's why, even with this super slow computer, and this is undeniably slower, right? These quantum computers will never be faster than NVIDIA's computer. It's just not possible. The gate speed is much slower. The throughput's much slower. It's just basically impossible to beat this number. Look how far the gap is already. And even if that gap would close, there's a lot of other problems like coherence and error correction and things like that. So quantum computers aren't faster than regular computers. They're just able to find one algorithm where you can go from this really big, difficult problem to a much simpler problem. Again, if you had some 10-digit number, or in fact, let's take a Bitcoin key. Why is this so important for Bitcoin? Well, if I take your average Bitcoin key, it's, like I said, 77 numbers. 77-digit number. And if you have the Bitcoin key for Satoshi's wallet, all you need is the number, and that's basically the password. It's a really, 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 really long number. And this is 10 to the 77th, roughly. And we all know the square root of something like this is just the exponent divided by 2. So the square root of 10 to the 77th is 10 to the 38th, roughly. So this is the amount of steps it would take to do. Now, even with an NVIDIA computer, even with 1 million NVIDIA computers, you couldn't do this. It would actually take longer than the amount of time in the whole universe. So it'd be impossible to do this on an NVIDIA computer. And you might ask yourself, well, how could we do it on the quantum computer if the quantum computer is slower than the NVIDIA computer? Well, at this one thing, it is not slower. It is a lot faster. Like I said, log of n cubed. Some people think it's a little bigger than this, but regardless, log of n cubed here is, a remarkably small number. The amount of operations is around, instead of 10 to the 38, it's something like 32,000 or maybe 320,000. So this is a real number a computer could do. And with 10,000 operations a second, how long would this take? 32 seconds. And we cracked Bitcoin. Amazing. Whereas it would take you until the end of the universe, possibly, if you're using NVIDIA chips, even if you're using the biggest fleet of NVIDIA chips. And how crazy is that? That we're doing the same problem. We're calculating the same exact problem. We're searching for a private key correspondence to a public key using an elliptic curve, and using one set of computers, we can't do it, but using a different set, a smarter method, basically, we can do it in just 30 seconds. So there's a really incredible, speed up that you get for certain problems. But the only problem where you get this massive speed up is this problem. Either factoring this very long number or taking the discrete log of a very long number, which is basically kind of an isomorphic problem. It's the same problem. There are no practical uses for this. For every other problem, quantum is the same speed algorithmically as an NVIDIA computer, except the actual wall speed or the clock speed of the computer for the NVIDIA is so much bigger that for 99.99% of all algorithms, you would never want a quantum computer. It can't do it. It's not faster. It's slower. It's only faster for this one silly problem. This silly problem is important to mathematicians, cryptographers, but it's not an industry. There's no way to speed up reality or something like that. So right now, this is it. It's been 30 years of researching quantum algorithms, and this is the only algorithm that has this massive speed up where instead of 10 to the 38 steps, we have just 300,000 steps. A computer can do this in 32 seconds, while the biggest computers from Microsoft, OpenAI, xAI, you took all their computers, combined them in one, and just threw them at Bitcoin, they still couldn't crack that problem in a million years. So, and it's just because this complexity shift. We go from O square root of n to O log of n cubed, which is much better. And you don't have this speed up for other algorithms. Like the binary sort thing I showed you, it's the same speed whether you use quantum, or it's the same algorithmic speed whether you use quantum or classical. But classical is so much faster. It's billions of times faster. There's no point to using a quantum computer for that. It would not help you. Some pundits would point to Grover's. There's a Grover's algorithm, but it's very slow, actually. It only goes from, it takes problems from O and n to O square root of n. This is not a big deal. This is not some huge help. And in fact, Grover's in practice is very hard to actually implement. It tends to be more of a theoretical thing. And that gets to some of the other problems with quantum. Well, even though it's only 10,000 hertz, which is amazingly slow, the system has decoherence. So the circuit can't stay in superposition for very long. Not only that, but there's no storage. So there's no RAM, there's no storage. So you actually have to find a way to write the circuit and put the data in. So you can't put, like, say, all of the internet or even a photograph into the quantum computer because there's no RAM. It only has so many qubits, and qubit can only store as much as a bit. So the NVIDIA GPU, of course, can store the whole internet and then some. And that's why it's useful to train neural networks. Quantum can't really help you there. There's nothing really that the quantum computer can do other than factor integers. And right now, we've tried all the quantum computers. The biggest integer we can factor is roughly 100,000 in that territory. It's nowhere near 10 to the 77th, it's 10 to the 5th. And you can go on AWS and try IonQ's computer. You can try IBM's quantum computer. And I've made videos about this on my live stream. I've live streamed it, but I'll make some separate videos that show that the biggest numbers you can factor are actually really small. So the current state of the art is pitiful. And I'm not sure that we're going to get to a 10 to the 77th or something like that very soon. I think eventually we will. Maybe 15 years from now, maybe 30 years from now. But we're only going to be able to run Shor's algorithm, which is not something that would support a really big market. So this is not the next NVIDIA. This is at best a very special instrument for cryptographers, maybe. Not a huge market because there's already ways to beat the quantum computer in cryptography. So the same mousetrap that was set up for the mouse, well, the mouse has figured out that this is a mousetrap that they want to maybe not, step into. And they've made a quantum secure, I don't know how to draw a mouse, it's got a tail. The mouse has it's terrible. I guess he's got whiskers. It looks like a centipede. There's already quantum secure algorithms, so we don't need to actually use these computers for anything. Even when they're able to factor Shors, we won't be using Shors. We won't be using integer factorization RSA or elliptic curve cryptography to protect our secrets anymore anyway. So in any event, I feel like, if you can point me to an algorithm that's really useful, that'd be great. But anytime someone tries to do that, I point out that there's no complexity speed up. Then this happens with D-Wave's computer, for example. Unless I can do something like this, where I go from O, a square root of n, which is slow, to O log of n cubed, which is super fast, why would a slower computer, a quantum computer, be faster than the NVIDIA computer? It can't be. Only under these circumstances where you have this shift, this complexity shift to a simpler paradigm. It's like a magic genie said, I know how to sort this much faster. You throw 1,000 thumbtacks on the ground and you've got to sort them in order or something like that. And a magic genie says, actually, I can sort those right away. Well, that's what a quantum computer can do, but just for this one thing. It can't do that for everything. Otherwise, we'd be really excited. AI companies would be excited. Businesses would be really excited. People would be trying to make quantum computers nonstop, and it'd be the most important thing ever. But the only thing it's good for, if you talk to people in the field, is Shors, at least right now. Could there be other algorithms? Well, it's been 30 years since Shors. So when are we going to get, a new algorithm that's really reliable like this, that's really fast? Because the current approach for some of these, of going from O of n to O of root of n, isn't that exciting. There aren't that many problems that suffer from this that we really need success with. So, that's my explanation. It's a little dense for why quantum computing is useless. But there is no algorithm that gives us much speed up other than Shors. And Shors is simply an integer factorization algorithm. It does not do anything else. So we'll get really excited when there's a new algorithm. But I also ask you, what do you want to compute? What do you really want to compute? And a neural network is something that we want to compute right now. That's kind of the biggest thing we want to compute at the moment. But neural networks require huge amounts of data. Right? You guys probably have heard of that, who has the data to train these neural networks, to train these AIs? It's all about the training data. And all that huge data has to go into the NVIDIA processor. But quantum doesn't have the room for this data. There's only maybe 1,000 qubit machine. That's literally 1,000 bits. You can maybe fit, your name in there. You can't fit all that data. 1,000 bits ain't much. What's that, 100 bytes? What's 100 bytes? What can you store in 100 bytes? You need terabytes, petabytes. I have a machine with terabytes of RAM. 100 bytes ain't going to help me. That's why this machine, people who understand quantum computing know that it's not good for much. We all want the next NVIDIA, but there is no next NVIDIA. There's not many things left to compute in the world. If they tell you something about traveling salesman problem, well, nobody needs to actually calculate the traveling salesman problem. And that's what Jensen said. Really importantly, at Quantum Day at NVIDIA, there's nobody sitting there saying, geez, if I had the answer the traveling salesman problem, I'd be so happy. So quantum is basically all a sham. If you have any questions, leave them in the comments. But that's my pitch. Right? We have to probably re-record that, but that's basically the gist of it. Really, Eric? Really? How much data can you put in a qubit? I'm pretty sure it's the same amount.